In this short video, we'll see an application of sub-Gaussian and sub-exponential distributions applied to the problem of dimensionality reduction. Right, so I initially introduced this in the previous class, towards the end of the previous class. So today I'll complete this particular application. So recall that the dimensionality reduction problem is the following. We're given n vectors, very high dimensional vectors, a1, a2 up to an, where each ai lives in some very high dimensional space, Rd, and here the assumption is that D is very, very large compared to n. So typically D is going to be much larger than n, and the goal is to do some kind of processing, some kind of data analysis or learning on this particular set of vectors that involves pairwise distances between these vectors ai and aj. Okay, and the complexity of computing, let's say, one pairwise distance is proportional to d. So obviously if d is very, very large, then the computational complexity is very high. Also, if you, let's suppose that we want to store these vectors in some particular form, the amount of storage space also grows linearly in D, so which becomes a bottleneck. So the dimensionality reduction problem is the following. We want to map these high dimensional vectors into some lower dimensional space. So from R to the capital D, we want to go down to R to the little d, where hopefully little d is much, much smaller than d. But in the end, we can't do this losslessly. It's not possible to do it without losing some amount of information. But recall that the objective of the data processing or data analysis or learning problem involves computing distances between these points. So hopefully the distances between the projected points, let's say g of ai and g of aj, should be roughly the same as the distance between the points ai and aj. Alright, so the goal is to design this map or a projection. It could be linear, it could be non-linear. So we want to design a projection that takes these vectors from R to the capital D down to the R to the little d, such that the distance between g of ai and g of aj is very close to the distance between ai and aj. So in particular, it is between 1 minus epsilon and 1 plus epsilon times the distance between ai and aj. So any map which ensures that the distance between pairs of points ai and aj is approximately preserved is called an epsilon isometry. So if the distances are exactly preserved, then such a map is called an isometry. This is not an exact isometry, it's only an approximate isometry. So we'll call this an epsilon isometry. Alright, so the key result that I want to prove is this very celebrated result called the Johnson-Lindenstrauss lemma. It says that we can choose this projection map to be a linear projection. So if we choose the vector, the map g of a to be some matrix x times the vector a, so the linear map is described by little d by capital D matrix, where each component is IID sub-Gaussian. We'll look at the parameters just a little bit. So each component is IID sub-Gaussian with certain parameters. We will see that later. Then and if we can choose little d to be some constant. This k is going to be the sub-Gaussian norm of each entry of x, and it depends on epsilon square. It depends on the number of points present in this particular set. So this should be capital N, and it depends on another parameter called delta. But this little d can be chosen independent of the dimension of the original space capital D. So if we choose d to be at least this much, then we can guarantee that with high probability, the matrix X, the linear projection X, is going to be an epsilon isometry. All right, and the probability that X is an isometry, as an epsilon isometry, is at least 1 minus delta. All right. And the result that we will use is something that we saw in the previous class. We saw that if x1 through xn are independent sub-Gaussian random variables, with each xi having zero mean and unit variance, but each component xi has sub-Gaussian norm equal to ki, then the L2 norm, or the L2 norm minus square root of n, is also sub-Gaussian. We saw this, and the sub-Gaussian norm is at most some universal constant times the largest of the ki squares. All right, and using this lemma, since the norm of X is sub-Gaussian, this implies that we can use Bernstein's inequality we can use Hoeffding's inequality to prove a tail bound on how well the norm of X is concentrated around square root of n. So the probability that the L2 norm of the vector X minus square root of n exceeds some delta, or in this case I take square root of n times delta, is upper bounded by 2 times e to the power of minus n delta square times some universal constant divided by k max to the power 4. Okay, let me sort of rewrite this. Instead of delta, I'll use epsilon, just to remain consistent with some notation that I will introduce later. Okay, so this is what Hoeffding's inequality guarantees us. Right, okay, so this is an epsilon square. So let me call this equation 1. We'll basically use equation 1 in order to prove the Johnson-Lindenstrauss lemma. Okay, so let's suppose that we take this matrix X. Let's go back to the setup of the Johnson-Lindenstrauss lemma. We have the projection G of A to be equal to X, matrix X times the vector A. Right, let me give a name. Suppose that I take the ith vector. So G of AI is equal to the vector X times the matrix X times the vector AI. Let me call this UI. Right, so UI is a random vector and the source of randomness basically comes from the matrix X. All right, so each UI can be written as summation L going from 1 through capital D of X I L times AI of L. Right, so this is, so AIL denotes the nth component of vector I, and XIL is the ith row nth column of the matrix X. So I have summation L equal to 1 to capital D X to L AIL. and so on, all the way up to summation L equal to 1 to capital D x little d times L times A I L. And this is my vector, the ith vector ui. Now what we want to ensure is that the norm of ui minus uj, which is nothing but the norm of g of ai minus g of aj. Alright, we want to make sure that this is within or this is approximately equal to the norm of ai minus aj. Right. So let's look at the vector ui minus uj. So ui minus uj, vector ui minus vector uj, is nothing but, since x is a matrix, this is x times ai minus aj, which is equal to summation L equal to 1 to capital D x 1L times AIL minus AJL up to summation L equal to 1 to capital D x little dl times AIL minus AJL. Alright. So if I want to guarantee that ui minus uj is, or the norm of ui minus uj is equal to the norm of ai minus aj, I have to select the components or the distribution of xij appropriately. Right. So let's see some intuition as to how to choose the matrix X, or the variances of the entries of X. So first let's start perhaps with expectation of norm ui minus uj the whole square. All right, this is nothing but summation L equal to 1 to little d. Let me write it the following way. Say summation m equal to 1 to little d expectation of summation L equal to 1 to little d x ml times AIL minus AJL the whole square. Okay, so I'll choose XML to be IID sub-Gaussian with mean XML to be equal to 0 and the variance of XML to be equal to sigma square. We'll see how to choose sigma square. So expectation of norm ui minus uj squared is going to be equal to expectation of summation m equal to 1 to d. Note that if each XML is a zero mean random variable and all of the XMLs are independent of each other, then the sum is going, the expectation of, I'm sorry, it should have been squared. Then this random variable summation L equal to 1 to d XML AIL minus AJL the whole square. So the norm squared is equal to XML minus XML times AIL minus AJL the whole square. This is the expression for the L2 norm square. So if XML are zero mean and variance sigma square IID random variables, then this sum is a sum of independent random variables, each with mean equal to 0. So the variance of the sum is nothing but the sum of the variances of these. So this is equal to just summation m equal to 1 to d, summation L equal to 1 to d, sigma square times AIL minus AJL the whole square. But summation L equal to 1 to d, AIL minus AJL the whole square is nothing but, so this quantity is nothing but sigma square times the L2 norm square of AI minus AJ. So this is equal to summation m equal to 1 to little d sigma square times the L2 norm of AI minus AJ square, which is nothing but d sigma square times AI minus AJ the whole square. Right? Which means that if I want the expectation of ui minus uj, or the, on average, if I want this square norm to be equal to this square norm, then I must choose sigma square to be equal to 1 by d. Right? So we'll choose sigma square to be 1 by d, or sigma equal to 1 by square root of d. Right, so X is a matrix with IID sub-Gaussian entries. XML, the sub-Gaussian norm is equal to some k. The mean of each XML is equal to 0, and the variance of each XML is equal to 1 by d. Alright, I can also write this as x equal to 1 by square root of d times the matrix y, where YML are all sub-Gaussian IID. YML has sub-Gaussian norm equal to, let's say, some k prime, right? Expectation of, so this is a zero mean random variable, and the variance of YML is equal to 1. Now, the reason why I'm choosing, I'm interpreting everything in terms of the Y matrix rather than the X matrix is because now the variance of YML is equal to 1, which means that I can choose the sub-Gaussian norm of YML to be some constant which is independent of little d. Right? Remember that there's an intimate connection between the variance and the sub-Gaussian norm. If I scale the variance by if I scale the random variable by some amount alpha, the sub-Gaussian norm also gets scaled by the same amount alpha. So I want the sub-Gaussian norm to be some constant independent of the dimensions and n and so on. Alright, and this choice of, and if I interpret everything through the matrix Y, then all of the parameters of the components of the matrix Y are constants which are independent of little d, capital D, as well as n. Alright, so now given this, I know that expectation, what we've just seen is that expectation of 1 by root d times y times ai minus 1 by root d times y aj, the L2 norm square, is equal to ai minus aj the whole square. What I want to know is what is the probability that so we'll do it step by step. What ultimately the goal is to find out what is the probability that g of ai minus g of aj, this L2 norm, is not within some epsilon times ai minus aj. All right. And this happens for any I not equal to j, right? So we want to ensure that for every I comma j, the distance between g of ai and g of aj should be within an within 1 plus or minus epsilon of ai minus aj. Let me, sorry, I made a mistake over here. ai minus aj should be greater than or equal to this particular quantity. Okay, so this is the quantity that we're interested in. So let's fix some I and j with I not equal to j based on what we've seen previously. G of ai g of aj minus norm ai minus aj greater than or equal to epsilon times norm ai minus aj, which is nothing but the probability that 1 by square root of d matrix y times ai minus aj minus L2 norm of ai minus aj greater than or equal to epsilon times L2 norm of ai minus aj. Just by sort of shifting things around, this is equal to the probability that L2 norm of 1 by norm ai minus aj times matrix y times ai minus aj minus square root of d greater than or equal to epsilon times square root of d. Alright, you can just, it's easy to verify that this whole thing, this 1 by ai minus aj times matrix y times ai minus aj, this is basically a matrix with IID entries, zero mean, unit variance, and sub-Gaussian, with the sub-Gaussian norm of each entry of this particular vector being equal to k. So this particular quantity, is a vector in r to the little d IID with zero mean, variance equal to 1, and sub-Gaussian with sub-Gaussian norm equal to k. Now I can apply this particular lemma that I had over here, right? I can apply this Hoeffding's inequality here to show that this is less than or equal to 2 times e to the power of minus some universal constant times d times epsilon square divided by k to the power 4. Alright. So the probability that the distance between g of ai and g of aj is not within 1 plus or minus epsilon of the distance between ai and aj for a fixed I comma j is upper bounded by this particular quantity. So what is the probability that g of ai minus g of aj, the distance between g of ai and g of aj, is too far away from the distance between ai and aj for some I not equal to j. So this is basically the probability that g is not an epsilon isometry for this particular set, right? A1 through an. Right, so this probability, just by a union bound, you take all possible pairs I comma j. How many pairs do we have? We have n choose 2 pairs times the probability that this does not happen for a fixed I comma j, for which I can use the above bound that we derived. 2 times e raised to minus some universal constant times d epsilon square divided by k to the power 4. Alright, which is at most n square times 2 times e to the power minus some universal constant times d epsilon square divided by k to the power 4. So if I want that G must be an epsilon isometry for A1 through AN with probability at least delta, with probability at least 1 minus delta, then what I want is that this quantity should be at most delta. Right? So what is the smallest d that is required in order to achieve this? Just by rearranging, I get 2n square divided by delta should be less than or equal to e to the power of c times d epsilon square divided by k to the power 4, or d should be greater than or equal to k to the power 4 times some universal constant divided by epsilon square times log of 2n square divided by delta, which is some universal constant times k to the power 4 divided by epsilon square times log of n by delta. Right? So in other words, I can do dimensionality reduction. I can reduce the dimensionality from capital D to a little d that is independent of capital D by choosing a random linear projection. And this random linear projection is going to be an epsilon isometry with probability at least 1 minus delta. Alright. So this is a very powerful tool. In practice, however, this is sort of a proof technique, and this basically tells you that if you choose, let's say, a random Gaussian matrix with IID entries, then you can, then basically this random linear projection is going to be an epsilon isometry with high probability. Now, this was a very early landmark result. And then there have been a number of improvements to this particular result. In particular, the one perhaps minor issue is that now X is an epsilon isometry, but in order to project down to the lower dimensional space, you have to choose. You basically have to do a matrix multiplication, right? You have to compute G of A times AJ for every vector AJ. And the overall computational complexity of finding x times a is basically little d times capital D, right? And that can be a bottleneck because now I still have a computation that is linear in capital D. So somehow I've not really got too much of a computational gain. I have got some savings in terms of storage space for sure. And if I want to do the same kind of, let's say, pairwise distances a number of times, then obviously I do get some sort of improvement. But I've not got a significant improvement because I still require this particular matrix multiplication. Right? But then there have been a number of further improvements made to this Johnson-Lindenstrauss lemma. You can show that it's possible to choose this matrix X to be such that this matrix multiplication, this matrix vector multiplication can be done very efficiently. In fact, you can choose this X to be such that this whole product can be computed in time d times log. So this computation can be done with computational complexity only order d times log of capital D. So there is a separate ensemble of matrices X that allow you to perform matrix multiplication using just this amount of computational complexity. There's a slight change, but not significant change to the little d that can be achieved, and you can still guarantee that X is going to be an epsilon isometry with very high probability. All right. So this dimensionality reduction is a very broad and active field, and many such results are known where you want to bring down the dimensionality from something that is very large to something that is as small as possible. In particular, you want the little d to be independent of capital D. That's if you can achieve that, then that's really the gold standard. Okay. So all right, so that's it for this particular video. In the next class, we'll look at a different class of concentration inequalities, more powerful classes of concentration inequalities, and some applications of those.